Okay, hello everyone. Nice to meet you all. My name is Meseret Birhane from Addis Ababa University, Ethiopia. And the impact of heat stress on livestock sector, evidence from large-scale data, is the title I'm going to present. It's going to work with my supervisor, Dr. Jonas Salem, from University of Gothenburg. The research question is, what is the impact of heat stress on cattle holding and milk production? And the motivation behind this study is studies suggest that the rise in human-induced global warming presents a substantial threat to life owners, and these dangers are particularly heightened in developing regions, specifically in tropics. And this prevalence in heat stress is expected to rise significantly in the future. So, given this fact, the livestock sector there are no many studies in livestock sector investigates the impact of heat stress on like milk production and livestock holding. However, livestock sector is an important sector which provides 70% global caloric consumption and 33% protein consumption for the globe. And it also offers 1.1 billion people employment. And the consumption of livestock-related foods are expected to grow exponentially in developing world. So, however, the livestock sector is this much important. However, studies related to livestock sectors are limited. So, what we did in this paper is identifying the impact of heat stress on cattle holding and milk production. So, to do so, we consider two broad outcomes. The first one is cattle holding in numbers, and the second, milk production in liters. And we expect to contribute three contributions. The first one is we expect to add the literature on the impact of climate shock. There are a large number of studies related to agriculture, specifically crop production, in both developing countries and developed countries. However, there are a limited number of studies regarding livestock sector. Second, we offer a developing country context using data from Ethiopia. Even if only limited number of economic research studies that investigates the impact of climate change on livestock sector, for instance, Key and Streaming, and Gisberg and Lin. All these literatures are focused on US, so this study will provide developing country context using data from Ethiopia, and Ethiopia offers the right setup because Ethiopia is highly vulnerable to climate change related shocks, and Ethiopia is the richest country in Africa and the fifth richest country in the world in terms of cattle holding. So this study will offer a developing country context. Third, many of the above mentioned literatures solely focus on milk production, and this study will provide the insight on the impact of heat stress on cattle holding, and it also explores the mechanism through which climate change affects livestock holding. So this study will expect to contribute all these three contributions. And to investigate the impact of heat stress on cattle holding and milk production, we used two independent data sets. The first one is annual livestock agricultural sample survey, which is conducted by Central Statistics Agency of Ethiopia, and it covers over 67,000 private peasant households each year, and it is a nationally representative data set. Since 2010, agricultural sample survey covers the same enumeration areas, but it resamples households each year. So this allows to create a panel data at enumeration area level. So this study uses a panel data from 2012 to 2016. And for final analysis, we use 10,654 enumeration areas for milk production and 10,844 enumeration areas from for cattle holding. The second data set is climate hazard central infrared temperature with station data set, daily set data set, which contains 2-meter daily minimum and maximum temperature and relative humidity from 1983 to 2016. And it is a 5 kilometer gridded data set. And after obtaining, we matched livestock data and climate data at district level. Then we calculate temperature humidity index. Temperature humidity index is a widely used measure for heat stress. A lot of literatures use THI as a measure of heat stress, and which defines a multi-phased phenomenon because caused by a complex interplay between different environmental factors like temperature, relative humidity, solar radiation, wind speed, so on. So to calculate temperature humidity index, we used a formula proposed by a National Research Center, and THI is calculated using this formula. T stands for temperature and RH is relative humidity. Then using THI, we next calculate heat load. And THI load is considered as a measure of heat stress, which measures the duration and the extent of heat load above a certain threshold. So for this study, we used a traditional threshold, which is 72 degrees Fahrenheit. So we consider a temperature above 72 degrees Fahrenheit as heat stress. And we assume to calculate heat load as daily THI follows a snake curve between the maximum and minimum THI over a 24-hour period, following set period and key and Slinger. So to calculate heat load, we should first calculate a maximum THI and minimum THI. So as we have a constant relative humidity, we solely focus on a maximum temperature and minimum temperature to calculate THI, maximum and minimum. So to calculate THI maximum, we use temperature maximum. To calculate THI minimum, we use temperature minimum. Then as empirical strategy, we used panel fixed effect. So we estimate our results based on this formula, and THI load measures humidity adjusted degree hours. So to calculate THI load, we used a formula proposed by Seth Perry, 2003. So in estimating the effect of heat stress on milk production and cattle holding, we assume that temperature below a certain critical threshold has no effect on daily milk production and cattle holding, following Key and Stringer 2014. So it means each additional degree hour below the certain threshold doesn't have any effect on either milk production or cattle holding. So we only focus on the negative effect of heat load on milk production and cattle holding. So this is a descriptive statistics. The average milk production is 1.3 liter, and total annual milk production is about 478 liters. Cattle holding is about 5, and the average heat stress is about 25. The next one is results. The first one is the impact of heat stress on milk productivity and production. So to estimate the impact of heat stress on milk production, we consider two outcome variables. The first one is daily milk production per cow, and the second one is total milk production per year. So as you see from the results, a 1 hour increase in heat load or heat stress decreases daily milk production per cow by about 0.7%, which is equivalent to a 1 day increase in heat stress decreases milk production by about 16%. And similarly, a 1 hour increase in heat stress decreases total annual milk production by about 1%, which is equivalent to a 1 day increase in heat stress decreases milk production by about 24%. Second, like after estimating the impact of heat stress on milk production and productivity, the next step we do is estimating the value of milk loss. So to estimate the loss, we followed the formula proposed by Seth Perry, 2003. The formula uses two meteorological parameters to THI diurnal cycle. The first one is THI maximum and THI threshold. As well, it uses duration D, which is also calculated by the formula proposed by Seth Perry, which ranges between 0 and 1. And we used this formula to calculate the value of milk loss. Loss equals alpha times maximum THI minus THI threshold square times D. Alpha represents the coefficient. So using this formula, we estimate heat stress reduces annual milk production by about 51 liter, which is equivalent to $34 per cow. So to calculate total milk loss value at country level, we used total milking cow information from livestock agricultural sample data for each year, and then multiplied by total milk cows by each year average milk loss data from the above equation. And finally, we multiply total milk loss by regional price, which is obtained from CSA, and we estimate total milk loss per year as 6,372,576,000 Ethiopian birr, which is equivalent to 358,263,490 dollars each year from 2012 to 2016 in 2012 price, which is a huge loss.
I had a question on the previous slide.
Okay.
So the number that you've calculated, what is that as a percentage of the milk production of Ethiopia?
Sorry?
What is the number that you've calculated for the loss of milk, what is it as a percentage of total milk production of Ethiopia?
Normally, I didn't calculate that one.
Okay.
Simply what I did is to estimate the amount of milk production per cow for per year, which is 51.
Mm-hmm.
Then I use this information and estimate the total milk production for the whole country using total number of milking cows information from this data set, and multiply that by regional price, and it gives me this amount as a total loss per year from 2012 to 2016.
I see, but because your estimates in the previous regression can just be driven by the fact that areas which are getting warmer, individuals in those areas are no longer holding cows, and areas which are not getting as warm, the cow holdings over there are increasing. As a result, there is a correlation, a negative correlation between temperature and milk per cow, but that is being driven entirely not by heat stress, but by purely, the dynamics of individuals adjusting. Right. So then it's possible that your estimates overestimate the amount of milk lost by the country as a whole.
Yeah, normally this milk loss is only solely depend on the difference between THI maximum and THI threshold, and the only thing we used is the estimated coefficient, which is alpha. So the loss is driven by the estimated coefficient, which we get in milk production data, the previous slide.
Okay, sure.
So the next step is the next one is the impact of heat stress on cattle rolling. So how increase in heat stress decreases cattle rolling by about 0.6%, or equivalently, a 1 day increase in heat stress decreases cattle rolling by about 15%. Then we estimate the impact of heat stress as a mechanism. We used a stock change to see the impact of heat stress on cattle rolling. So we consider like cattle births, cattle days, cattle selling and buying decision, and disease as a mechanism through which heat stress will affect cattle rolling. So heat stress significantly affects births and cattle days, and it doesn't significantly affect selling and buying decision of rural peasants. And the impact on cattle days is unfortunately unexpectedly negative, but statistically insignificant. So heat stress affects cattle rolling through reducing cattle births and increasing cattle days. So we consider a decrease in cattle births and increasing the cattle days as a mechanism through which heat stress affects cattle rolling. Then we estimate heterogeneous effects of cattle rolling, heat stress on cattle rolling by different ages. And we consider 5 groups. The first one is less than 6 months cattle. Second, between 6 months and 1 year. Then 1 up to 3 years old cattle, 3 to 10 years, and greater than 10 years. So heat stress significantly affects young cattle relative to others. The effect on heat stress on less than 6 months cattle is like a 1 hour increase in heat stress decreases cattle less than 6 months by about 0.8%. And the effect is also similar, negative and statistically significant for between 0 and 6 months and 1 year, as well 3 to 10 years. However, the impact of heat stress on cattle between 1 year and 3 years are negative but statistically insignificant. However, the impact of heat stress on those cattle greater than 10 years are positive and statistically significant. This might be due to the fact that this cattle due to the fact of like adaptability capacity. So cattle above 10 years may have like overtime adaptable capacity. That might be the reason it becomes positive and statistically significant. Then we estimate the impact by purpose. So we consider 5 different purposes: cattle for beef, breeding, dairy, draft, and others. And the impact is negative and statistically significant for beef, breeding, and draft purpose cattle. However, the impact is negative but statistically insignificant for dairy. It is unexpected, as the impact on milk is negative. And the impact on other cattle groups are positive and marginally significant.
Say you've got 1 minute left.
Okay. Ella?
All right, I was just saying you have 1 minute left. You can keep going.
Okay. Then we estimate the heterogeneous impact effect due to time constraints. I'll pass it. Then we estimate the impact by season. So we classify heat stress into 4 seasons: fall, winter, spring, and summer. For milk production, the impact is only statistically significant for fall seasons. For cattle holding, the impact is negative and statistically significant for fall and summer seasons, and positive and statistically significant for spring season. Then we add lag THI, and the impact on meat production is statistically insignificant. However, the impact on cattle holding is negative and statistically significant. This is due to its effect on cattle birds. The impact of lag heat stress on cattle birds is statistically significant. It's expected because consumption is is done at lag season. Then we estimate nonlinearity effects. So animal scientists describe or categorize heat stress into three categories, even above the threshold, as low, medium, and high. So we used those categories to estimate the impact. And for milk production, the impact is statistically significant for medium and high heat stress. However, for cattle holding, the impact is only statistically significant for higher heat stress. Then we also estimate the nonlinearity effect. So to estimate nonlinearity, we used mean THI, and we classify into different beans based on being up. And as you see in the graph, like the impact is almost negative, and it becomes statistically significant at between 70 to 72 THI beans. So the assumption we made in empirical strategy almost holds. The effect is only statistically significant above the certain threshold. For cattle holding, the effect is almost similar. Up to a certain threshold, the impact is almost zero. And above that threshold, the impact becomes negative. And as the temperature, the THI increases, it becomes severe.
I'm so sorry, but you're out of time. Could you wrap up?
Okay, robustness check and conclusion. Heat stress affects cattle holding, and the impact is huge. On the increasing heat stress reduces milk production by above 15% and cattle holding by 15%. And the mechanism is cattle birth reduction and cattle days. It's all. Thank you.